Hello everyone. So in the last video we have seen till here that how to check whether a given number is prime or not, with how to prime factorize a given number. So now we are doing it for a range, like we are given a range, in between we are given multiple integers. We need to tell that these are primes or not. So for this we have Sieve theorem, and first of all I am discussing the Sieve theorem, then I am discussing a modification of Sieve theorem. So let's get started. So for that, let me write the Sieve theorem's function first. So obviously we are returning a vector of boolean that this number is prime or not, for every prime from 1 to, for every number from 1 to n, right? So function name is Sieve. We are taking a upper limit n that we need to calculate till here, and now obviously we are making a boolean array, and let's call it n with n plus 1 element. Initially everything is false. Now let's edge 1 is not a prime, so let's make it true. Here one thing you should notice is we are indicating every prime number with false and every non-prime number as true. So if number is prime, then vt represented by false, and if non-prime, then we will represent that with true. Alright, so let's go ahead. 1 is not a prime, so I made it true. And now let's start a for loop from 2, and it will go till n, and over here we start a for loop from I square. Why it's I square I will be explaining soon, and then it will go till this. We do j plus equal to I. So what we are doing is we are initially set that all the numbers are prime between 1 to n, right? So what I'm saying is every number from 1 to n is prime initially, right? They all are prime. Now what I'm doing is I'm coming on to an integer, like 1 is not a prime, so I deleted it from the vector, or you can say I made it true. Then I came on to 2. So what I'm doing is I'm going on to 2's multiple, that here we have a 2's multiple 4, then we have 2's multiple 6, and so on. So what I'm saying is if some number that is a multiple of some other number, then that this number can't be prime anymore because it has a divisor like 2, right? So what I'm doing is I'm taking a I and going to its multiples and making them as non-prime. So I'm going on to its multiple and making them non-prime. So let's make them non-prime means true. As I said earlier, we storing non-prime as true in the vector, right? Before that we have should include one condition, that if that ith element is not prime, then only go on to this, otherwise there is no, that making no sense, right? Because if we go to 4's multiple, they are already included in 2's multiple, right? So we don't need to go on to non-primes multiple, right? So for that we can include a simple code over here, right? So if it is prime, if I is prime, then go on to its multiple and make them as all as non-prime. So okay, we made that all as non-prime. Now it's okay, and then at the end just return the VT array, right? Now let's call it by inputting n, then we call Sieve with n, that is a greater limit, right? Now what we are saying is we are given n as a upper limit, and we are given multiple numbers in between 1 to n, and we need to print that they are prime or not. So let's print for all the number from 1 to n whether that is prime or not, right? So if what I can say is pool vt equal to this, if vt of I not equal to mean it's prime, so say that I is prime, right? Else say that I is not a prime, alright, and then we will be returning. I think we did it right. Let's check it out. One test case, and the higher limit should be 12. So 1 is not a prime, 2 is prime. Why it's printing 1 1 1 1? Okay, I printed 1 over here. Let's go ahead. So 1 is not a prime, 2 is prime, 3 is prime, 4 is not a prime, 5 is prime, 6 is not a prime, 7 is prime, 8 is not a prime, 9 is not a prime, 10 is not a prime, 11 is prime. So it is giving right answer. So now we can calculate, we can tell for any integer from 1 to n that whether it is prime or not in just of one time, right, by calling vt of I. Now this is one form of Sieve theorem that we generally use it for primes, calculate if there are multiple number given to us and we need to find that they are prime or not. But now we have a modification of Sieve theorem. What I'm doing that because I need to calculate factors of prime factorization of n, and same problem that here we are doing for only one integer. Now let's see, I given multiple integer from 1 to n and I need to tell that what is the prime factorization of the given particular number from 1 to n, right? So what we can do is, instead of bool we can store something in it, right? What we are storing, first of all, 0 represents that this number is prime, right? So 1 is not a prime, so I would say key 1, and then let's go ahead. If it is vt of I is 0, then we will come inside, means if it is prime then come inside. And what you need to do is, here you just need to store I. Why I'm storing I? Let's see, how can I explain. Let's see key I equal to 5 initially, right? Then if 5 goes inside, then what that said is, let's say it's 2 and I equal to 2, right? This I equal to 2. If I go inside, then it said to 4. Okay, vt of 4 should be equal to I, means 4. So I is 2, so I stored 2 into 4, then it goes to 6, then it will say like, okay, vt of 6 is equal to 2, then vt of 8 is equal to 2. But it is actually, it is the smallest prime divisor of the number, right? So we are storing, for every number we are storing smallest prime divisor of that number inside the vt, right? At the end we return vt. And now let's make it long as it's returning it, right? So now let's see key. I need to count, need to print the prime factorization of some given number in 1 to n range. So first of all, what I'm doing is I'm taking that how much integers are there. So for that we need to give m, then we need to give m integer to print their prime factorization, right? So what we are doing is we go till m, then we do I plus plus, and we will input the integer, and now we need to do its prime factorization, right? Why it's showing me red? Okay, it's not a vector of bool, it should be vector of long, right? Now what I say is, while vt of x not equal to 0 means if it is not a prime, then what we need to do is we just need to print the smallest prime factor of this by vt of x, and now we need to divide x by that smallest prime factor, right? Now x will be modified, and at the end, now if x is a prime, so it is a prime factor of its own, so we need to print that as well. And here we go. Let me give a space over here. I think we are all set. Let's run it up. What is the way to give input? One is for test cases, here it is t test cases, then n is the maximum range till where we need to count. So let's see, I give it 20, then we are giving m integers to it, to their prime factorization. Let's say I give 5 integers. I need 10's prime factorization, I need 12's prime factorization, I need 8 prime factorization. Okay, 1 20 20 is n, right? And then 5 is m. Alright, then I give 10, then we'll give 8, then we'll give 6, then we'll give 12, then we'll give 5, and it is all 5. Let's see what it does. Okay, initialized it with 0, vt of 1 equal to 1. If vt of I is 0, I is starting with 2, going ahead, j plus equal to I plus plus go till end, vt of say, okay, taking x as input, then vt of x not equal to 0. Okay, so I can't take one thing to be noticed here, right? I can't take 1, and I till m, taken x as input, vt of x not equal to 0, till then keep going, x divide equal to vt of I, got, it should be vt of x, right? Let's run it again. So for 10's prime factorization is 2 into 5, 8's prime factorization is 2 into 2 into 2, 6 prime factorization is 2 into 3, 12's prime factorization is 3 into 2 into 2, 3 into 2 6, 6 into 2 12, right? 5's prime factorization is 5 itself. So in this way you can answer the range. Like earlier what we are doing, we are calculating prime factorization for each number, right, individually. Now what we are doing is we are calculating prime factorization for whole the range, and it will take I think if every divisor is 2, then it will take log of n time, right? And if we do individually, then that function will take root of n time, right? So edge log of n time is better than root of n time, right? Yes, because 10 to the power 6 root is what? 10 to the power 6 root n is 10 to the power 3, and that is greater than log of 10 to the power 6 for sure, right? So this is a optimization if we need prime factorization for multiple numbers, so we can go for modification of the Sieve theorem, right? And if we need to know about prime numbers in a given range, then we also go for Sieve theorem. There are multiple more modification of Sieve theorem, so you can study them at your own, I think. So thank you for watching. We will be coming with another videos on Euclidean algorithm and torrent functions, modular arithmetic, and everything. So stay tuned for that. Thank you for watching.